Hello everyone, thank you for being here. My name is Stephen Changcherta and together with my colleagues Stephen Nathaniel and Rafael Putra Wijaya, we'd like to present our work titled Generalized CNN for Detecting Malaria Infected Cells in Blood Smears Image. This is our submission for ICORIS from Group 17 of BINUS University School of Computer Science. To set the stage, malaria is still one of the world's most serious public health problems, causing hundreds of thousands of deaths every year. The key to saving life is fast, accurate diagnosis, but that's exactly where many endemic regions struggle. Today, the gold standard for diagnosis is a manual microscopy, where a trained expert examines a blood smear's image under a microscope. It works, but it's slow and labor intensive, and depend on the skilled microscopists who simply aren't available in many of the areas that needed them the most. This is where deep learning comes in. Conventional neural network or CNN can automate this detection accurately and quickly. Architectures like ResNet 50, EfficientNet B3, and Exception make point-of-care diagnosis realistic. And just as importantly, they can be tuned to minimize false negative, which directly protect the patient. So why this study? We identified three gaps. First, manual diagnosis doesn't scale. It cannot keep up with the large screening programs in high-volume endemic regions. Second, while CNN model for malaria is already exists, they vary widely in accuracy and computational cost, and there's no standardized benchmark to compare them fairly. And third, very few studies systematically compare lightweight CNN architecture on a large balanced dataset to find the model that best balance accuracy with efficiency. That gap is what we set out to address. Our approach has three steps. In the first step, we systematically compare three advanced CNN architecture, ResNet 50, EfficientNet B3, and Exception, each with its own strength in feature extraction, efficiency, and accuracy. In the step 2, we apply transfer learning using ImageNet pre-trained weight combined with standardized processing, preprocessing, and data augmentation to help the model generalize across diverse blood smear samples. And in the third step, we evaluate everything on the niche malaria cell image dataset using rigorous metrics, optimizing training with the Adam optimizer, binary cross entropy loss, and callbacks like early stopping and reducing LR on plateau. Here's our pipeline from end to end. The input is GM-sustained blood smears image collected from a niche dataset containing both parasitized and uninfected cell in preprocessing. We normalize the pixel, resize image to a standard size, and subtract the ImageNet mean for consistency. The CNN preprocessing stage apply transfer learning across our three architectures using pre-trained weight, and the output is a binary classification, infected versus uninfected, together with a confidence score that support clinical decision making. Now, I'll hand over to my colleague to walk you throughout our hypothesis and methodology.
Okay, thank you, Stephen Chang. Now we are going to see our research hypothesis. So our guiding hypothesis is this. Among the three architectures, the lightweight CNN that strikes the best balance between diagnosis accuracy, and a minimal false negative rate will be the most clinically viable for automated malaria detection. More specifically, we expected efficient B3 to come out on top. Its compound scaling method and optimized design give it a strong features extraction with excellent computational efficiency, which makes it especially promising for resource-constrained clinical settings. Next, a bit on methodology. Our dataset is the NIH malaria cell image that contains 37,558 samples that are perfectly balanced, 13,779 parasitized, and 13,779 uninfected. We split it 80% for training, 10% for validation, and 10% for testing. For training, we use binary cross entropy loss with Adam optimizer at a learning rate of 0.01. We add early stopping to prevent overfitting and reduce alarm plateau for adaptive learning. Transfer learning with ImageNet weights was applied across all models, and augmentation was performed dynamically during training. Next, on the technical side, our pre-processing pipeline includes normalization, resizing, ImageNet mean subtraction, while augmentation, random flips, rotation, zoom, and shift helps reduce overfitting. The three architectures differ in the key way. ResNet 50 relies on skip connection, EfficientNet B3 use compound scaling, and exception use deploy separable convolutions. For evaluation, we use comprehensive set of metrics like accuracy, precision, recall, specificity, F1 score, and AOC ROC. But our most critical clinical focus was minimizing false negatives because a missed malaria diagnosis can be life-threatening. With the methodology covered, I'll pass it to present our result and recommendation to our friend.
Okay, thank you, Stephen and Nathaniel. Now to the results. Efficient MB3 was our best performer, achieving 97.50% of accuracy, an F1 score of 97.49%, and an AUC ROC of 0.9965. Most importantly, it only produced 37 false negatives, a low level enough to be clinically meaningful. And it wasn't just one model. Resnet 50, Efficient MB3, and Exception all exceeded more than 90%, 97% on accuracy on the test set, which really demonstrates how effective transfer learning with pre-trained CNN is. That said, the ROC curve analysis confirmed EfficientNet B3 superior discriminative ability as combination of high accuracy and minimal false negatives made it the standout choice. And now we move to this is the ROC curve. We move to the analysis and conclusion. To interpret these findings, efficient B3 across the board, and the low false negative count of 37 is what matters most clinically because minimizing misdiagnosis is essential for patient safety and timely treatment. More broadly, our study validates that lightweight CNNs with transfer learning can effectively automate malaria diagnosis from blood smear images. Because these models are computationally efficient, they are well suited for deployment in resource-limited settings, offering a reliable, scalable screening solution for the regions that need it most. And then we move to the recommendation. First, deploy efficient MB3-based screening tools in endemic and resource-constrained areas and integrate them with mobile microscopy devices for true point-of-care diagnostics. Second, future research should add attention mechanisms to improve interpretability, expand toward multi-class parasite stage detection, and keep validating on real-world data for robustness. Third, collaborate closely with healthcare providers to fit these tools into existing clinical workflows, because adoption is what ultimately improves patient outcomes. With that, thank you for listening to our presentation, and we'd be happy to take any questions. And goodbye. Is there something wrong?
Oke sih menurut saya mah.
Stop